Hi everyone. So I'm just going to cover the Abdullah. Maheen, can you hear me? I'm just going to cover mass spectroscopy in this particular class, and so it's a topic that's just been recently added to ACE. It was part of A2, and it usually came with NMR spectroscopy, which is not in your course. So you don't really have AS past paper questions dealing with mass spectroscopy. There are a few questions in the specimen paper, but we'll be referring when we do past papers. We'll be doing A2 past papers, and remember that NMR spectroscopy is not in your course, especially if you're doing AS. Mass spectroscopy is. So the first thing I'm going to talk about is what's mass spectroscopy and how does it help you. So the problem. So the first thing is when you discuss analytical chemistry. You want to analyze molecules. You've got molecules, and molecules are mostly invisible. Like if you have vinegar, you can't really see the structure of vinegar. That's ethanoic acid or acetic acid. So you can't really tell what the vinegar molecule looks like. You can't even see molecules under microscopes. So how do you figure out that the structure of ethanoic acid looks like this? So the bits and pieces of information is like solving a puzzle, and every technique, whether it's infrared or NMR spectroscopy or mass spectroscopy, and many other techniques like electrophoresis and even chromatography, etc. They provide you bits and pieces of information about a particular molecule. And so, what information does mass spectroscopy provide about a molecule? Because remember, it's an invisible molecule, you can't see it under a microscope, and you have to figure out what the structure of the molecule looks like without. So, you're basically blind to it, you can't see it. So, you have to somehow figure this out by getting some tiny bits and pieces, some information, some clues about the molecule. So the mass spectroscopy gives you this idea that it provides you with the number of carbon atoms. You can figure out the number of carbon atoms by looking at a mass spectrum. You can figure out the MR of the molecule, which is the relative mass of the molecule, and some information could be derived about the structure, which is based on the fragmentation pattern. You can figure out the number of Cl and Br atoms. So what happens in mass spectroscopy is that spectroscopy, like if you look at this molecule over here, let's say we have a CH3Cl molecule. Now this molecule, and remember we don't know what it is. We're completely blind to it, so we can't see it. So let's assume I've taken this molecule and I start bombarding it with electrons. There's a beam of electrons. I'm bombarding it and smashing electrons into it. That's my ionization chamber. What will happen is this CH3Cl, it might it might ionize. It might lose an electron as I am smashing it with electrons, lots of electrons. So it might end up losing electrons and it might form a +1 ion. So the whole molecule will be intact, except that it would be in the form of an ion, and that is referred to as the molecular ion. That the molecule is completely intact, but it's in the form, it's ionized. What other things could happen is, as I'm smashing it with electrons, what other things that can happen is that the molecule might break down into smaller pieces. So the molecule and the smaller pieces, remember, is going to be a piece of this bigger molecule. So maybe what happens is that this CH2 breaks off and it turns into an ion, CH2 +1. Or what could happen is that your CH3 breaks off, and that could turn into a CH3 +1 fragment. So these are bits and pieces of the bigger molecule. And the fragments, remember, the fragments are you could have a CHCl piece breaking off. So the fragments are always a piece of the original molecule. So all sorts of tiny pieces. Whenever you smash things break down into pieces, and this is exactly what happens here as well. So tiny pieces, tiny ions are produced, but these are fragments, small fragments. The heaviest one, so you have particles of different masses that are being produced in this ionization chamber. The heaviest one is your molecular ion. That's the biggest one because the whole molecule is intact. And then you'll have these lighter versions, smaller pieces, which are going to be smaller fragments. What you do now is you've got a bunch of charged particles, and these charged particles are converted into a beam. Now, one question over here is, ठीक है, Abdullah, is this clear? Is this ठीक है? ठीक है. So one thing that happens here is that one very important piece of one thing that happens over here is one question that arises is, why is this always plus one? The thing is, it's not always plus one. It could be plus two ions as well. It could be minus one ions as well. It could be neutral fragments as well. So the positive charge, it's not always plus one. It could be minus one. I mean, you're smashing electrons, so it could gain electrons. It could lose electrons. It could lose 2 electrons. It could lose 3 electrons. Any sort of ion can be produced. But the mass spectrum focuses on the plus one ion. It filters off all the other ions. So we're also focusing on only the plus one ions. The negative ions that are produced, the other all sorts of other ions that are produced, we just ignore it. We just focus on the plus one ion. So, anyways, these particles are converted into a beam, and the beam is passed through a magnetic field. And as charged particles pass through a magnetic field, what happens is they start getting deflected. And remember, deflection is inversely proportional to mass. As you know, the left-hand rule in physics, charged particles that travel through a magnetic field, they're going to get deflected. Now, the deflection is inversely proportional to mass. What that means is that heavier particles are going to be deflected less, and lighter particles, these ones, the fragments, the tiny fragments, they're going to be deflected more. So you're going to be getting your heavier particles, and these heavier particles would be deflected less because they're heavy. The lighter particles, smaller fragments, will be deflected more. So you've got detectors over here that are detecting these charged particles that are hitting them. Now, the heaviest one is your molecular ion. That's your big one. That's your heaviest one. But there would be 2 different particles that you would call your molecular ion. CH3Cl plus 1, there'll be 2 different detections. Why? Because one of the particle would be deflected more, it would be slightly lighter, and one would be deflected less, as it is going to be slightly heavier. So the deflection, as a first thing, why do you have 2 different particles? The reason you have 2 different particles is that chlorine has got 2 different masses. Chlorine has 2 isotopes, and those isotopes are really abundant. Chlorine is 35 and chlorine is 37 as well. So you've got 2 different masses, and they're very abundant as well. Chlorine is 35 is 75%. Chlorine 37 is just 25%. So that means that if you detect any 100 particles of chlorine, there would be 75 of them would be 35, 25 of them would be 37. So the reason the molecular ion has 2 different deflections is that one of the molecular ion is going to be slightly lighter, because if you total up the masses, carbon is 12, hydrogen is 1, and Cl is 35, and Cl could also be 37. So one of the molecular ion would be slightly lighter, so it's going to be deflected more, and one of the molecular ion would be slightly heavier, so it's going to be deflected less. And the probability of getting Cl35 is 3 by 4. So getting this molecular ion has a probability of 3 by 4, and getting the other molecular ion has a probability of 1 by 4. Technically, this is known as the molecular ion peaks, which are known as the M peaks. The lighter version is known as the M peak. And heavier isotopes, the mass increases. In this case, the mass increases by 2. So the molecular ion, this peak is known as the M plus 2 peak, because there's a difference of 2. So this is a notation that is often used, that lighter particles have a mass of M, and the lighter molecular ion will be called M, and the heavier ones would then be called M plus 2. If the mass had increased by 4, you would call it M plus 4. So that's a notation that is often used. Now, the way we figure out the relative masses of molecules is through this deflection. Like, you can compare it to carbon 12. I mean, if you remember the definition of atomic mass and molecular mass, you're always comparing it to carbon-12 isotopes. So this is how you figure out the masses of particles. This is so basically you're focusing on the deflection, then you convert it into mass. By looking at the deflection, you can figure out what the mass of the particle really is. Anyways, so your mass spectrum would look like this. It's going to look like this. This is going to be the abundance of the particles, or the proportion of particles, the number of particles that you're getting. So you'll be having detections. This axis is mass m over e or m over z, where e and z are basically charges, which is +1. So basically, this axis over here is, basically mass. So you have a detection at 50 and you have a detection at 52. The heaviest ones are your molecular ions. And then you'll have all sorts of lighter particles that are getting detected. So those lighter particles would be your fragments. Now, our focus at the moment is your heaviest particle. That's your molecular ion. I'm going to focus on that. Remember the probabilities that 3 by 4 is the chance of getting 50 and 1 by 4 is the chance of getting 52. Why was there a difference that's because of Cl. So when you detect these particles, there's going to be more of 50 being detected. Cl35 has a greater abundance. So, you'll get more chances. There's more chances, 3 times more chances of getting Cl35 compared to Cl37. So the relative peak areas, or the relative heights of these peaks, 50 is going to be your M peak, 52 is going to be your N plus 2 peak. And the relative height would be 3:1. And then you have all sorts of fragments. The fragmentation has no specific pattern because when you're smashing molecules, any sort of small piece could be produced. Some would be produced in greater quantities, some would be produced in lesser quantities. So, and every time it's going to be different. So fragmentation really doesn't really have any specific pattern, but the molecular ion will have a pattern. And this is something that you should remember. That's it. This is basically the crux of it. The explanation, all of this is not important. All you have to remember in your exam is that if you have a mass spectrum and it looks like this, and there are two heaviest peaks, the molecular ion peaks, and they have a difference of 2, you have an M and you have an M plus 2, and the ratio is 3:1, that clearly indicates the presence of a single Cl atom. So that's it. That is all you have to know. So in your exams, this is all that's going to come. That when you see MM plus 2, whether it's a chromatogram mass spectrum that's given on a graph drawn like this, or whether they've just stated it that the MM plus 2 ratio is 3:1. And remember, the ratios, 3:1 is the same as 9:3, or it's the same as 300:1000. So make sure you understand what 3:1 is. They wouldn't write it 3. Maybe they'd say 42:14. That's also 3:1. So, but as long as it's 3:1, that means 1 Cl is present. That's it. Things are going to be very simple. The question is going to be extremely simple. That's about it. 3:1, it's got 1 Cl that is present. So then, moving to the next one, we'll do bromines as well. So let's move to that. But now in the new syllabus, they just talk about MM plus 2. So we just need to know 1 Cl present. But in the previous A2 exams, like in the previous years, they also talk about the presence of 2 Cls. So this is, we're going to do this tentatively because they've just changed this right now. So maybe they might ask you about this. The syllabus clearly doesn't mention N plus 4 actually. So the 2 Cl thing is we're just doing this tentatively. So I'm just going to do the same thing that we did earlier. So let's assume that a molecule now has 2 Cls. So a molecular ion in the ionization chamber would be produced, and that's going to be your molecular ion. It's going to have 2 Cls. And there would be lots of tiny fragments. The molecule will break down into smaller pieces, and lots of fragments are going to be produced. So you've got lots of tiny fragments. And you pass these charged particles through a magnetic field, and they get deflected. So when they get deflected, now again the focus is on this molecular ion, the heaviest ones, the ones that are going to be least deflected. Now, since the molecule has 2 Cls, this one, we don't care about the fragments. The fragments are the lighter ones. So I don't care about the fragments at the moment. So if I have two Cls, what's going to happen? What's going to happen is that if I have two Cls, the molecular ion will have three different masses. There would be three different particles that would be referred to as the molecular ion. Either both Cls are 35, so that's 112. That gives you an MR of 112, relative mass of 112. So that's your lighter version, that's M peak. Then one of the Cls could be 37. That would give you the N plus 2 peak. Because if you take it as 37, one of the Cl as 35, then the mass would come out to be 114. Or pair, you've got both Cls could be 37, the mass would come out to be 116. So M peak plus 2, that's M plus 2 peak, plus 4, that's M plus 4 peak. So 112, 114. So this thing over here has three different masses. It's got three different masses. Now, since it's got three different masses, I'm going to calculate the probability of getting both Cls as 35. What's the probability of getting 112? What is the probability of detecting this particle? So what was the probability of getting Cl as 35? That was 3 by 4, right? I mean, we did this earlier. In the previous case, I told you. The probability of getting Cl35 is 3 by 4. The probability of getting Cl37 is 1 by 4. So let's have a look at this. So dono Cl35, 35 and 35, that's 3 by 4 into 3 by 4. That, I mean, if you Cl35 and Cl35, basic probabilities are going to get multiplied. That's 9 by 16. Both of them as 37, Cl37 and Cl37, both of them, that's 1 by 4 into 1 by 4. That gives you 1 by 16. What is left is the other one, 6 by 16, or you can calculate this. It's 35 and 37. 35 is 3 by 4 and 37 is 1 by 4. Or it could be the other way around. 114 can also be obtained if the first one is 37 and the second one is 35. So there are two scenarios. Either this is 35 and this is 37, or the first one is 37 and the second one is 35. So if you do 3 by 4 into 1 by 4 plus 1 by 4 into 3 by 4, that gives you 6 by 16. Or simply you could have done is you could have subtracted 9 by 16 and 1 by 16 from 1, and you would have gotten 6 by 16. So that's the probability of this one. So you don't even have to know all of this. All you have to know is what are the chances of getting the M peak, what are the chances of getting the M plus 2 peak, and what are the chances of getting the M plus 4 peak if there are two Cls present. So the mass spectrum would look like this. It's going to be 9:6:1. So 42, the M peak will have a higher probability, the M plus 2 will have a lower probability, 6, and 1 by 16 for the N plus 4 peak. So whenever you see a mass spectrum, and you have different molecules, any molecule could have two Cls. So whenever you have a mass spectrum and it looks kind of like this, it's 9:6:1, the three heaviest peaks, the molecular ion peaks, then that means the molecule has two Cls. That's about it. That is what you've got to remember in this case. And that's kind of it in this case. So I'll move to the next one now. और हाँ ठीक है तो clear है. So we're gonna move to the next one now, which is चलो आगे चलते हैं. अच्छा, so this one, and there must be a summary written over here. This is all you got to remember. That's it. I mean, all the explanation, that's kind of pointless because the question isn't even going to go in depth into this. I mean, all the explanation that I did is kind of pointless. They're not going to ask you. All you got to know is if a molecule has one Cl, its molecular ion peaks, there are going to be two of them, M and M plus 2. They're going to have a difference of 2, and the relative probabilities or heights would be, or the detections would be 3:1. M would have a 3 times higher chances of getting detected. If a molecule has two Cls, then because of the two Cls, you're going to have M plus 2 and M plus 4, and the relative probability would be 9:6:1. So this two Cls thing is, we're doing it tentatively because all previous A2 past paper questions had two Cls in it, but they've not written this in this new syllabus, so we're just going to do this tentatively. Now the same thing can be done with bromine as well. Let's move to bromine now. So the same thing, exact same thing could be done with bromine, because bromine has isotopes as well, and there are two of them, 79, and there's another one which is 81, and the relative probability is 50%, 50% chances. That's 1 by 2 and 1 by 2, so they have equal probability. So you're going to do the same thing. Everything is ditto, exactly the same. I mean, that's the summary, but I'm just going to quote it over here. Uh, so I'll just do, it's exactly the same thing, except the probabilities are different. So you have a molecule of bromine and it's got just one bromine. So if it has one bromine, the molecular ion will have two different masses. It could either be 79 or it could be 81. So if I sum up the masses, it's going to give me 94. It could also give me 96. So there's going to be an M peak and there's going to be an M plus 2 peak as detected on the mass spectrum. And the chances are the same. It's 1 by 2 and 1 by 2. So they have equal probability of getting both of them. So it's 1 by 2 and 1 by 2. So it's going to be look like this. So that's when you have, I mean, this kind of indicates, let me write this over here. Whenever you see this thing and you've got M and M plus 2 peak and they have equal heights, the heights are 1:1. So that means the presence of 1 BR. So 1 BR is present in the molecule. Secondly, what if a molecule has 2 BRs and you do mass spectrum, you do the whole thing that we did above, and this is going to be the molecular ion. There would be 3 different types of molecular ion, because the bromine could have different masses. It could have both of them as 79. So it's going to be 14 plus 79 plus 79. That gives you a mass of 172. That's the lighter version, M peak. The M plus 2 slightly heavier. That's has a bromine which has a mass of 81. And then you've got a molecule which has both bromines as 81. That's 176. So you've got M plus 2, and M plus 4. So there would be 3 different molecular ions that would be detected with different masses. And the relative probability would be, what's the probability of getting both of them as 79? That's 1 by 2 into 1 by 2, 1 by 2 chances into 1 by 2 chance. What's the probability of getting both of them as 81? That's 1 by 2 and 1 by 2. What's the probability of getting one of them as 79 and the other one as 81? So it's going to be 1 by 2 into 1 by 2, or it could be the first one could be 81 and the second one could be 79. That would also give you 174. So the 2 probabilities are going to get added up, and it's going to be, and this would come out to be, if I sum this up, this comes out to be 1 by 4. And this one comes out to be 2 by 4. And this one comes out to be 1 by 4. Again, so the relative heights are 1:2:1. So again, 2 bromines, that is tentatively. We're doing this tentatively. So the explanation is kind of irrelevant. The probability thing is kind of irrelevant. All you have to, the questions would be very simple. All you have to remember is, if a molecule has 1 BR, it's going to have an MM plus 2 ratio of 1:1. And if a molecule has 2 BRs, it's going to have an MM plus 2, M plus 4 ratio of 1:2:1. But this one is, again, 2 BRs not mentioned in syllabus anymore. So we're just doing it tentatively. So, but this is only, you'll see the questions. The questions are going to be extremely basic. They're going to be very basic. That's about it. Now, the third thing, the last thing that you're going to talk about when you're doing mass, we can leave that. You can also figure out the number of carbon atoms, and the number of carbon atoms can be figured out by using this formula. I'm going to come back to this formula later, but let's focus. How do we figure out the number of carbon atoms? Now, the way you figure out the number of carbon atoms is that carbon has 2 isotopes. One is 12 and the other one is 13. So mainly the isotope is 12. That's 98.9%. Or we can just call it 99%. We can round it off. And there's 1% chance of getting carbon 13. So it's 99:1. So out of 100 particles, 99 of them would be carbon 12. Just there's 1% chance of getting carbon 13. So if I do a mass spectrum of a molecule that has only 1 carbon atom, it's got only 1 carbon atom. So if I do a mass spectrum of this molecule, so just 1 carbon atom, remember that. So what's going to happen is that it will have a mass of 16, because carbon would be 12 and the hydrogens are 1 each. Or it could have a mass of 17 as well, because carbon could be 13. So what's the relative probabilities? 99% chances that you're going to get carbon 12, and there's only 1% chance of getting carbon 13. So that means this has, the ratio is 99 ratio 1, like 16, the particle with the mass, the molecular n, and this is going to be called n plus 1 because the difference in mass is now only 1. So you'll have an m peak and you'll have an n plus 1 peak. And the relative heights would be 99 ratio 1. For every 99 particles of m detected, there would be just one particle of m plus 1 detected, because it just has a probability of 1%. So how does that help you? Let's move to carbon 2. What if a molecule has two carbons? So if a molecule has two carbons, what will happen now is that it's going to have an M peak, which is that both carbons are 12 and there are 6 hydrogens. Or it could have an M plus 1 peak, that one of the carbons is 13 and the other one is 12, and 6 hydrogens, that's 31. Could also have an N plus 2 peak, 13 and 13, both carbons are 13, and there's 6 hydrogens, that's 32. So there are 3 different masses. Now I'm going to try and calculate the probability. So what's the probability of getting both carbons as 12, carbon 12 and carbon 12? So that's probability is getting multiplied, and that gives me 98%. So see what happened. When you had a molecule had one carbon, the M had a higher probability of 99%. As the number of carbon atoms increase, what's the probability of getting the M peak now? Carbon 12 and carbon 12, that's 99% into 99%. That gives you approximately 98%. So what is happening here? As the number of carbon atoms are increasing, the probability of getting the M peak is now slightly lesser. And the probability of getting the M plus 1 peak is slightly higher now, because if you calculate carbon 13 and the other one is carbon 12, or the other way around, the first one is carbon 12 and the second one is carbon 13. So 98.9%, that's carbon 12. The second one, 1.1%, that's carbon 13. Or the other way around, so that's 2 scenarios, that's 2%. So from 99 ratio 1, it has now changed to 98 ratio 2. We don't talk about the M plus 2 peak because the probability of getting the M plus 2 peak is very, very low. I mean, both of them as 13, that's 1% into 1%. That's hardly detectable. That's a very low probability. So we won't be detecting any particles with N plus 2 because the probability is extremely, extremely low. So let's see if the trend continues. What if a molecule has 3 carbon atoms? So if it's got 3 carbon atoms, then you'll have an M peak that all 3 are carbon 12. That's carbon 12, carbon 12, carbon 12, and 2 oxygens and hydrogen. So that gives you 74. So what's the probability? 99% into 99% into 99%. That approximately gives you 97% now. So the trend is following. And what's the probability of getting the M plus 1 peak? That's one of them would be 13. So it could be the first one or the second one or the third one. So there are 3 scenarios. So it's 1% into 99% into 99%, and it's into 3, because there are 3 different scenarios. That gives you 3%. So we can look at the trend now. So the trend is, you've got 1 carbon atom in the molecule, the M plus 1 ratio would be 99 ratio 1. You've got 2 carbon atoms in the molecule, the ratio would be 98 ratio 2. And you've got 3 carbon atoms, the ratio would be 97 ratio 3. So you can guess the other one, 4 carbon atoms, that's 96 ratio 4. So the M plus 1 ratio can simply give you the number of carbon atoms. By just looking at this ratio, you can figure out the number of carbon atoms in the molecule. So you see 97 ratio 3, that's fine. That's whenever you see 97 ratio 3, that clearly indicates that's 3 carbon atoms. But the problem with ratios is that ratios can be quoted in many different numbers. Like 48.5 ratio 1.5 is the same as 97 ratio. It's the same as 97 ratio 3. So if you want to figure out the number of carbon atoms, all you have to do is use this formula, that's it. So the explanation that I just did, it's completely irrelevant. All you have to do is use this formula. Then you can figure out the number of carbon atoms based on the ratio, M plus 1 ratio M. You plug in the ratio into 100 over 1.1, whatever number you get rounded off, and that's the number of carbon atoms. So for example, we had a ratio of 48.5 ratio 1.5. I put it there in the formula, 100 over 1.1 into M plus 1 divided by M, and I got 3 carbon atoms. So So you're gonna use this formula. I mean, this one I did it. I did this for this one. 97:3 is the same as 48.5:1.5. The confusion would be they wouldn't write 97:3. They might give it in some other form. So just remember this. Uh, just remember this formula. That's kind of about it. That's about it. So I'm just going to now show you some questions. We're going to try and do some questions. Hopefully, we're not running out of time. So let me just open questions. I think they're already there. Just one second. So remember, the questions would be extremely basic. तो ये मैं शेयर करता हूँ. Brief. ठीक है, so this, let me share it again. The other one. एक सेकंड अब्दुल्ला. So window NMR. ठीक है, here we go. आ गया. अच्छा, अब यहाँ पे ना questions. Let's do a few questions. And remember, the questions are going to be extremely basic. Here's the first one. Calculator nikalo, ठीक है, that's the first one. So if you look at this question, forget the other questions. These are A2 questions. So you don't really need to know anything else. So these are A2 questions. Just a second, hang on. Achha, these are A2 questions. So that's it. I mean, you're given the M plus 2 peak. So that's what is it? What's the formula? Number of carbon atoms. You can figure out the number of carbon atoms by doing what? 100 over 1.1 into M plus 1. M plus 1 they've given as 0.9. And M is given as 20.4. So all you have to do is I'm going to open the calculator now. I don't know what the answer is. So let's just open the calculator, do this, and that's it. That's the number of carbon atoms. That's going to be 100 divided by 1.1. वो गया फिर into 0.9. फिर divided by 20.4. 20.4. So 4 out of 4. That's 4 carbon atoms. That's it. Or M की value जो ना, that's the MR. Remember, the molecular mass is the MR. The MR of the lightest version of the molecule with the smallest isotopes or the lightest isotopes. So ये हो गया बस और तो कुछ NMR spectrum, that's not in your course, so forget that. Your questions would be kind of very basic. So let's do another one. Here's another one. M plus 1 ratio is given. So what you got to do is you got to figure out the number of carbon atoms. So we're going to figure out the number of carbon atoms. It's going to be 100 over 1.1 into 0.15 and divided by 4.5, right? So you do that, you'll get the number of carbon atoms. That's 100 divided by 1.1 into 0.15 divided by 4.5. That gives me three carbon atoms, right? So 3 carbon atoms aa gaya, bahar khatam. And most questions are going to be, I mean, all of this is not in your course, so ignore that. That's A2. Let's keep doing a few more questions. So let's keep doing a few more questions. You've got another one, which is this one, M plus 1. So 100 over 1.1 into 2.5 divided by 74. Okay, I mean, the M plus 1 ratio is given. So ये वाला करते हैं, that's 100 into 2.5, and then it's going to be divided by 1.1, and then it's going to be divided by 74. So 3 are that's 3 carbon atoms. Okay, the ratio is given over here. That's M plus 1 ratio. So kind of really easy. It's really easy. Let's find chlorines and bromines. Let's see if there's a question. In A2, they used to have this with NMR spectroscopy, but that's not anything that you have to do. So AUC and MM plus 2, they gave you the MM plus 1 ratio. That's 43.3 ratio 3.35. you can find the number of carbon atoms. But here you've given the m plus 2 ratio over here as well. And the ratio you see, it's 43 ratio 14. I mean, you're going to figure out the simplest ratio first. How do you figure out? I mean, this is m and this one is m plus 2. So how do you figure out the simplest ratio? The way you figure out the simplest ratio is divide by the smallest. So if I do 43.3 divided by 14.1, that kind of gives me 3.07, and this is 1. So it's basically 3 ratio 1. So what did we talk about in 3 ratio 1? That whenever you have an mm plus 2 peak and it's 3 ratio 1, that means there is exactly 1 Cl that is present. Okay, there's exactly 1 Cl present. Or, so that's it. Explain what is indicated. It's got 1 Cl, that's it. Let's do another one. Let's see if we can find someone with, I think that's still mm plus 1. So over here, you had m plus 2 peak. I mean, if you focus on this part. So over here, again, the mm plus 1 is given. You can figure the number of carbon atoms. The m plus 2 ratio is given. And they're saying that they have similar height. When they have similar height, that means 1 bromine is present. That's about it. So you got 1 bromine that's present. So let's find another question in the old A2 papers. So nothing here. This one, mm plus 1 ratio, that's again just find the number of carbon atoms. So here they're talking about what would be the difference in the ratio of mm plus 2 peaks if the pesticide contained 1 chlorine. If it's got 1 chlorine, then remember the mm plus 2 ratio would be 3 ratio 1. And if there's 1 bromine, the mm plus 2 ratio would be exactly the same, because both bromines have equal probability. Over there, they're talking about 2 chlorines. So we did that, 9 ratio 6 ratio 1, right? But if 2 chlorine atoms are present in a molecule, the mm plus 2 ratio and m plus 4 ratio would be 9 ratio 6 ratio 1. So we did that. But this one, I think, is now not part of the syllabus. So, but it's kind of easy. You just have to remember this. So, I mean, tentatively just remember it. So just wanted to see a few more mm plus 1 again. Here's he talking about natural bromine consists of 2 isotopes, bromine 79 and 81 in roughly equal proportions. The mass spectrum consists of 5 peaks. So here you have so he's talking about identifying the species as 5 peaks. Remember BR2? So the first one would be that when you ionize this, it's going to form a molecular ion, which is Br2 plus 1, or it might break down into smaller pieces, and the smaller piece is just going to be a Br atom. So how many different types of Br2 plus 1 can you have? You can have Br2 plus 1 where both of the Brs are 79. So it will have a mass of 158. You could have a Br2 plus 1 where one of the Brs could be 81. So the mass of bromine molecule would be 160 in that case. And you could have a heavier one, which is that both bromines in the molecule are 81. So that will have a mass of 162. So there would be 3 molecular ion peaks. This would be your M peak, the lighter version. This is going to be your M plus 2, and this is going to be your M plus 4 peaks. वो बाकी दो कौन सी हैं? The other two belong to this Br plus 1. There's a Br plus 1 as well. So there would be 2 Br plus 1 ions detected. One would be slightly lighter, 79. One would be slightly heavier. So he's asking, suggest the mass numbers of the 3 peaks and suggest the ratio of the abundance. We did talk about the ratio that what's the ratio of getting the mm plus 2 m plus 4? If you have, it's 1 ratio 2 ratio 1. We did calculate this in the notes over there. So 1 ratio 2 ratio 1. And what's the probability of getting Br plus 1, 79 and 81? The 2 lowest masses, they would have equal probability. It's going to be 1 ratio 1. They have equal chances of getting detected. So that's about it. Let's see if we spot any other question. No, we don't. So I'm just going to move on now to the next part, and let me दूसरी screen share कर लेते हैं. So let me continue with fragmentation now, very quickly. So I'll just do fragmentation, which is also एक second share कर लेगा. So now we're going to talk. So this one. So now, if you can see the screen, TKP Ajat here. Say this one. I said, let's talk about. I said, remember this summary. That's it. Again, summarizing. 1 Cl, mm plus 2, 3:1. 2 Cls, tentatively mm plus 2, m plus 4, 9:6:1. You have to remember for bromine, one molecule of bromine, that's one atom of bromine in the molecule, that's mm plus 2:1:1. If you've got two bromines, that's going to be mm plus 2, m plus 4, and the ratio is going to be 1:2:1. Or the next part is this one, number of carbon atoms. Mn plus 1 ratio, 100/1.1. That gives you the number of carbon atoms. That's it. So we're going to briefly talk about fragmentation now. Okay, I'm just going to briefly discuss fragmentation. And to discuss fragmentation, just 1 second, let me. So a lot of things are jumbled up. So let's focus on this. So I'm doing a mass spectrum of this molecule over here, which is CH3, CCl3, and that's a molecular end. So the focus is now on these tiny fragments. You've got tiny fragments. You've got CH3 plus 1, C plus 1, CH2 plus 1. All these tiny pieces of this bigger molecule. Now, these tiny pieces are going to be detected at lower masses. Like carbon will be detected at 12. CCl3 will be detected at CCl2 will be detected at 84. And so tiny and smaller masses, you're going to get all these smaller fragments. Now, there's a lot of information that's hidden in these fragments as well. You get to know a lot of information about the molecule, about the structure of the molecule. For example, I mean, if you identify like a puzzle, like if you've got this big molecule, and if you start talking about the smaller pieces give you a lot of information. For example, there's a question over here, and the question is like this. Or we can directly jump to questions, just to explain how these smaller particles are going to help you detect the molecule or figure out the molecule. So I'm just going to jump to questions, and I'm going to tell you how smaller pieces give you a lot of information, a lot of very valid information about the structure of the molecule. तो वापस उसी sheet पे कर लेते हैं कि we can just have a quick go through on some of the questions. ठीक है, NMR spectroscopy. So the question is, for example, so the question is now going to be focusing on fragmentation. So here's one. Okay, they're saying draw the structure of the intermediate A and so this one. Let's focus on this question. So they're saying that there's a molecule which is 2,3-dibromo-propan 1-ol. So let's draw that propan 1-ol. That's propan 1-ol. And it's 2,3-dibromo. So 2 pe bromine, and 3 pe there's a bromine. And you've got all these H atoms. So this is 2,3-dibromo propan 1-ol. So what are the fragments? You could have all sorts of small pieces breaking from this molecule. They could be a CHBr piece that's breaking off, right? So you could have, and remember when you write fragments, always write a positive charge next to it. So that could be one of the fragments. Any fragment could be produced. any small piece of the bigger molecule that could be produced. Now the question is about identifying the molecular ion. Uh, Identify the molecular formula, including isotopic composition, where element of these six peaks. So you're getting these fragments, and you're being asked to identify this. So I'm going to go for 31 first. What could be 31? What fragment will have a mass of 31? So 31, I think, is this one. Not really sure. 31 CH2 OH plus 1. Is that 31? That is 31. Oxygen is 16. Carbon is 12. So 12 plus 16, and there are 3 hydrogens. So that's 28 plus 3. So that is 31. So we figured out what 31 is. Then you're getting a detection at 106. So what could be 106? 106 could be, let me make a hunch. Is this 106? For this, I would have to use my calculator. Is that 106? That could be a fragment. So that's 12, carbon 12, plus hydrogen is 1 plus 1. Plus bromine is either 79 or 81. That gives me 93, actually. So I need a slightly bigger fragment. Let's say my fragment is slightly bigger. Let's say it also includes the neighboring carbon atom. So now what do I get? Is this 106 or not? So carbon plus 2 hydrogens, that's 14, plus that's bromine, that's let's take that as 79, plus the other carbon, that's 12, plus 1 hydrogen. So 106, I'm getting 106, exactly 106. So it is CH2, Br, and CH plus 1. And the Br over here is the 79 one. It's 14 plus the 79. They're also asking about the isotopic composition. So you have to tell them that I'm taking Br as 79. And then there is carbon, and then there is another hydrogen. So that's 1. So that is 106. So I figured out 106. Same way I can figure out 108. That's very easy. Just take the other one. That's 81. So it's going to be the same one. It's just going to be 81 over here. Now, what is 185, 187, and 189? That, I think, is the molecular ion, because it's coming out to be in 1 ratio. I mean, look over here. It's 1 ratio, 2 ratio, 2 ratio 1. So 2 bromines, that is what you are supposed to get. So this one is the molecular ion. That's the whole ion with a positive charge. So these 3 belong to the molecular ion. The lighter one is when you have both bromines as 79. The slightly heavier one is 1 bromine is 81, and the heaviest one is that both of your bromines are coming out to be 81. So that one is. So we're running out of time. एक तो ये हो गया. Let's try and find another question, a slightly more difficult question. There was one. I don't know where it went, but we're running out of time. Let me. ठीक है अब्दुल्ला, बस खत्म कर रहे. So let's find some more. I said, let's. This one. I'll just quickly explain what this question is all about. They're saying, like, if you read the question, they're just saying that you've got Si, X, Cl is Y, and oxygen is Z. I mean, they've stated that. And they're saying that the only isotopes that you have is oxygen is 16. So oxygen could be 16 only. Chlorine is 35. And Si is 28. There are no isotopes. So that's it. They did the mass spectrum and they found something at 133. They found something at 149. Something at 247. They got a detection at 263 and one at 396. And what happened was this one would be the molecular ion. So what they're asking for is, in this question, what they're asking for is, you're supposed to draw the structure of each of the particles, 133, 263, and hence suggest the displayed formula. So what you're going to do is, you're going to start with the simplest one, 133. What could be 133? Like there's this big molecule over here. 133 is going to be a small piece, a smaller tiny version of this small tiny version of the bigger molecule. So that's 133. So 133 ka pata lagana hai. What's 133? That's so if you just look carefully, it's probably going to be one Si and three Cls. That is what 133 looks like. Like Si is 20, you have to do some trial and error. It's not that easy to figure out what 133 is. I just knew it, that's why I wrote it down. But and we're running out of time as well. But you have to do trial and error, and it has to make sense. Like bonding wise, the structure has to make some sense. So silicon is 28, 35, 35, 35. That gives you exactly 133. Now there's a slightly bigger fragment. That's 149. So remember, the bigger fragment is always contains the smaller fragment as well. So 149. What is 149? 149 would be a slightly bigger fragment. The difference between 133 and 149 is 16. So there's a difference of 16. So that indicates that if I add an oxygen to it, that will make it 149. So that's basically my 149 now. Then there is 247. Now the difference, 247 is a much bigger fragment. So the difference between 149 and 247 is of 98. And so I have to figure out, I need to add 98 to this. I'll get to 247. What is 98? 98, if you do trial and error, it's going to be one Si and two Cl. So basically there's an Si and there's a Cl. If you add them to this, that would give you 247. And then you have 263. That's again a difference of 16. So there's a heavier fragment by 16. So that must be having an oxygen. So that's 263. And then 396. The difference between 263 and 396 is 133. So that means there's another SiCl3 being added to it. So that's your molecule. So I've done this very quickly, but this was a very difficult question. So all you had to do was you had to figure out 396, the bigger molecule. The smaller fragment was this one. Then there was a slightly bigger fragment, which was 149, and that was this one. Then there was an even slightly bigger fragment, and that was 247, and that was this one. Then you had 263, that was an even bigger fragment, which was this one. And then finally you had 396, so which was your biggest fragment, which came out to be this one. So do we have time still? Just hold on 1 second. Still a few minutes. So I'll do another one, which is right at the beginning. Now, another thing about fragmentation, hopefully that question is clear. You're going to get questions similar to that. Now, one thing about fragmentation is, and let me discuss that. There was a question somewhere over here. This one. So one thing about fragmentation is, ignore mass spectroscopy, NMR, that's not in your course, that let's say you figured out that it's C3H6. You figure out the number of carbon atoms, you figure out the MR, but you're getting two isotopes. You don't know which one is which, right? Because C3H6, you did mass spectroscopy, you figured out C3H6, but you don't know which one is the right one. C3H6 could be an alkene, a straight chain alkene, or it could be a cyclic alkane as well. So based on the shape of the molecule, the fragments would be different. For example, in this case, you're going to get a fragment of CH3. Now, mass spectrum doesn't really differentiate, like it doesn't know whether it's CH3 or not. It tells you the mass, that you will get a detection at a mass of 15, which is CH3. But over here, you're never going to get a particle which has a mass of 15, because you're either going to get a fragment which has a mass of 14, or you might get a bigger fragment which has a mass that is going to be, that would, like if it includes the neighboring carbon atom, that would be a lot greater than 15. So no particle at 15 detected. So mass spectrum can help you identify, because based on the shape of the molecule, you're going to get some fragments in one isotope, but not in the other one. So CH3 fragment can never be obtained. A mass of 15 can never be obtained over here in this particular molecule over here, because there is no CH3 in this case. So you would be able to figure out that C3H6 is this one, and not the other one, based on the fragmentation pattern. If you don't detect anything at 15, then that's this one. If you detect something at 15, then that means it's this one. So the fragmentation pattern can give you some clues about the structure, which structure is present in one of them and which structure is not present in the other one. चलिए ठीक है, लेट्स ये बस इतनी क्वेश्चन है, ये टाइम अब खत्म हो गया, तो बस अब अगली दफा ही कंटिन्यू करते हैं, लेकिन इसमें हमने बस सारा कवर कर लिया, ठीक है. इसको जाके देख लेना. I'll send you the worksheet as well, and but just remember it's going to be very basic. Most of the stuff is kind of really basic for mass spectroscopy. वो बस याद रख लो, रट्टा लगा लो, mm+2, mm+2, m+4, ठीक है. वो कार्बन आटम्स का फॉर्मूला याद रख लो, 100/1.1 into m+1/m. एक्सप्लेनेशन पीछे कोई नहीं पूछने वाला, ठीक है, उसकी कोई खास आपसे पूछता नहीं है एक्सप्लेनेशन. बाकी रह गया आपका ये फ्रैगमेंटेशन. तो फ्रैगमेंटेशन वो फ्रैगमेंट आइडेंटिफाई करने वो कह देगा ज्यादा से ज्यादा, ठीक है. या फिर वो फ्रैगमेंटेशन से ना आप डिफरेंट आइसोटोप्स में फर्क पता लगा सकते हो, कि अगर आपको पता लग गया कि C3H6 है, ये नहीं पता कौन सा वाला C3H6 है, तो फ्रैगमेंटेशन एक में फ्रैगमेंट जो बनेगा वो दूसरे में नहीं बनेगा, ठीक है. सो यू कैन गेट एन आइडिया ऑफ व्हिच पर्टिकुलर आइसोटोप इट इज. सो दैट्स अबाउट इट. चलिए ठीक है, लेट्स एंड दिस. और ये खत्म हो गया, इसमें कोई ज्यादा सोचने की बात नहीं है, ठीक है. इट्स जस्ट वेरी वेरी बेसिक. चलिए, ओके एवरीवन, टेक केयर.